that was loud. As Hyoung said, I'm the resident IT support, but I also happen to be a PhD student here at the Australian National University, the Research School of Astronomy and Astrophysics. And today I'm going to be talking to you about my recent work with the upcoming Funnelweb Star Survey and how that relates to exoplanet characterization. So, a bit of an overview about what I'm going to be talking about. So Funnelweb is a survey that will be starting next year, and it will observe millions of stars in the Southern Hemisphere over the next few years. How this relates to exoplanets is quite simple. The better we know a star, the better we know any planets that are orbiting it. So what we plan to do with Funnelweb is any star that we observe, we're going to produce a spectral library for all stars. And what I mean by this is we're going to produce stellar parameters for the stars themselves. So these are things like the temperature of the star, the metallicity of the star, abundances, and the surface gravity, so essentially how inflated the star is. So one of the ways we aim to do this is with a data-driven approach. And what I mean by this is essentially machine learning. So by using this method, we can avoid the limitations associated with theoretical models and spectral line lists, but a little more on that later. So back to how all this relates to exoplanets. So knowing what kind of host star you are dealing with is critical. As an example, M-dwarfs are great for exoplanet research because due to their smaller masses and smaller radii, our searches are more sensitive to Earth-like planets in the habitable zone. Contrast this with M-giants, which are awful at that because planets in the habitable zone on short periods would actually be inside the star, which is really bad. So by knowing the surface gravity of the star, we can make more targeted searches and look for those stars that are more likely to have Earth-like planets. And so moving forward, Gaia parallaxes will help with this issue, but still having spectral indicators of gravity is important. On the planet side of things, density is an important physical parameter that tells you what kind of planet you're dealing with. So what I've got here is a similar plot. We've probably seen one like this over the past few days. So on the x-axis, I have the semi-major axis, so the separation between the sun of the star and the planet. On the y-axis, I have the planetary density. The color bar is the metallicity. And on the y-axis, just off to the left, I've got 4 solar system planets. Only one of which I could actually put on this plot because the semi-major axis doesn't go far enough out to put them all on there. But by knowing the density, we can get an idea about planetary populations. And so the important thing here is that we observe certain things through, say, transit observations. And so stellar radii come from knowledge of a star's luminosity and its effective temperature. And luminosity, we need to know the distance as well. And to get a planetary density, we need to know the ratio between the star and the planet. So the better we get these parameters, the smaller the errors on the planet parameters. So spectra also gives access to the stellar composition. So again, this is what the color plot was telling us. And finally, having precise densities helps with constraining eccentricity, which can tell us something about planet formation or the history of the system. So with all that in mind, back to Funnelweb. So what I've got here is an image. It's a GIF. It is moving. It might not be that visible from the back of the room, but so Funnelweb is capable of observing 150 stars at once by robotically positioning optical fibers known as starbugs. And this is what is called the Taipan instrument. So the automation of these starbugs, their quick configuration time, and the short exposure of the survey means a data volume of about 1 million stars per year. So as to what we're actually going to look at, so the main Funnelweb survey will be everything in the Southern Hemisphere off the plane and brighter than the Gaia magnitude of 12.5. We're also going to have supplementary surveys that make up for some populations that don't quite get into those bins, such as fainter M-dwarfs or young stars. And so the aims are high signal to noise and the aforementioned spectral libraries, which I talked about. So now back to the limitations with theoretical models. So modeling stars and their myriad spectral lines is difficult, especially when you do it in 3 dimensions and don't make various simplifying assumptions. So I want to briefly touch on why Funnelweb won't be, well, at least the method I'm intending to look at won't be using such models. So what I have here is a HR diagram from Bansby et al. And they used a 1D approach, so a one-dimensional analysis using the ionization balance of two ion species. What we see here, so this is the HR diagram with effective temperature on the x-axis and surface gravity on the y-axis. And what we see here is the low mass stars should come down here, but instead we end up with a flat main sequence. We haven't correctly, or they haven't correctly estimated the surface gravity. So if we were to employ such techniques with funnel web, these issues would be propagated to thousands or tens of thousands of stars. So by employing a data-driven approach where we use standard stars, we hope to avoid issues such as this. And I keep saying data-driven, but I'll actually explain what it is now. So I'm using data-driven and machine learning interchangeably. And essentially what we have here is, think about it as a black box. The specific algorithm isn't important, but what we do is we take our observations, and in this case, it's the spectra of stars. And what I want to do is train an algorithm to take the input of our observations and give us the output of the parameters of the star, so temperatures, metallicity, etc. So if we have a bunch of standard stars that we know their parameters really well from the literature, we can train our algorithm. And then what we can do is we can take the stars that we don't actually know anything about, put them into the algorithm, and we can get stellar labels for all the stars that we've observed, regardless of whether we had precise values from the literature for them before or not. So the benefits of such an approach is that it is model and spectral line list independent. And so this frees us from the simplifying assumptions that I mentioned, such as dimensionality effects or non-LTE effects, which could go on to influence future classification. Instead, our accuracy is derived from stellar standards, but this is also its principal limitation in that if we want accuracy, we need these standard stars to span our parameter space. So we want stars with all sorts of combinations of metallicity and surface gravity, effective temperatures, etc. And so our requirements end up being sort of strict, but we do want to be as model independent as possible. So that's, at least with this method, that's what we're aiming for. So by way of example, what are a few sources of M-dwarf standards? So M-dwarfs are, common but faint stars, and they have complex atmospheres. And so there's a relation to get the effective temperature of a star if you know its luminosity and its radius. And we can measure radii for these stars using interferometry. And this allows us to precisely get the effective temperatures of the stars. I mentioned that they have complex atmospheres, so they're harder to measure than, say, FG or K stars. But what we can do is get infrared spectra, high resolution, of these stars, which is a better probe of metallicity. Or, alternatively, we don't measure the metallicity of the M-dwarf itself, but if the M-dwarf has a parent star that is, say, easier to measure, we can measure the parent star and make the assumption that stars that are born together share similar metallicities and apply that to the M-dwarf. And the same thing goes for M-dwarfs in clusters. And so finally, we have M-dwarfs in a system known as a double-lined eclipsing binary. And essentially what this is, it's a binary star system where the stars are similar enough in brightness that you can make out spectral features from both stars. So one star isn't completely washing out the light from another star. And here I've pictured as an M and an N pair, but it doesn't necessarily need to be that. But we can get radial velocity measurements of these stars and transit observations, which allow us to precisely constrain both the mass and the radius. And so the binaries will pose a problem for a data-driven approach, but it's still important to make sure that they are observed with funnel web to see what we can do with them. Now, in terms of the specifics of the algorithms that we're going to use, there's a few options. So one from the literature is known as the Cannon, named after the astronomer Annie Jump Cannon, who also classified stars without the aid of theoretical models. So the Cannon, what it does is it takes input of your entire spectrum, like you imagine the chip of your CCD, and you've got spectral pixels. So each spectral pixel will be described by a quadratic function. And by doing that, it's able to pretty precisely get back the parameters of the training data set. And so it was trained on the Apogee survey, which was mostly giants, and they get accuracies of 1.5 to 2%. But the principal limitation of the Cannon is essentially its simplicity, in that quadratic function will suffer when trying to describe complex physics over the whole parameter space of the HR diagram. So another algorithm that we will be looking at, it has a very jargony name, semi-supervised local tangent space alignment. But the idea is the same principle. We take the spectrum of the star, and if you consider each pixel to be a dimension, we have a very multi-dimensional data set. And what we have here is a demonstration of this algorithm work. So here we have spatial coordinates mapped onto like a truncated donut shape. And by using this algorithm, we can unwrap the surface of the donut and still preserve information. And so instead of unwrapping spatial coordinates, we're unwrapping spectral coordinates into the stellar parameters. We should be able to get back stellar labels. And so, unlike the Canon, this will be more complex. So we'll be investigating both methods in Funnelweb. But that's pretty much it. So I've listed some summary points right on time. And spoken about Funnelweb, its utility for exoplanet characterization and research, and our classification approach, and hopefully things are a little more clear than they were 10 minutes ago. I know on the weekend at the school, there was talk of having cats in your slides because it's also an astrobiology conference. I don't have any cats, but the Funnelweb logo is a spider, which is approximately a cat if you can't count and you don't know what a skeleton is. Anyway, that's it.